Pre-calculus students, welcome to your 10.1 notes. We're going to take a look at limits today, new topic. Hope you enjoyed the little YouTube clip from one of your favorite movies, one I've actually never seen, but I'm sure it's great. So, hey, let's get started here. We're going to talk about limits. Now, truthfully, this is essentially the first chapter of calculus that we're talking about today. But the concept of limit, it's fundamental to that study of calculus. So let's start with an idea. You've seen questions like this before. Find the maximum area for a rectangle that has a perimeter of 28. So we know to find perimeter of a rectangle, you take 2 times the length plus 2 times the width, and that would equal 28. And maybe more fitting in this particular case, if we're trying to find lengths and widths that would work, we could say length plus width would have to equal 14. So I'm going to just create a little table with length, width, and total area. And we're going to just start plugging in some numbers to see what we come up with. So we could start with something like the length is 4. So if the length is 4, the width would have to be 10, and you can debate with me if length should be longer than width or not, but that's fine. And in this case, the area would be 40. But then what happens is, as we get a little bit closer to the length and width being the same, you can see that we have an increase. So an increase in area, I should say. With 6 and 8, our area is 48. Now, instead of going straight to 7, though, what I want to show you is what happens when we get close to 7, like 6.5 or 6.9. And we'll go a little bit beyond 7 as well. I'm actually not going to even plug in 7 because I think you guys know 7 would be 49. But 6.5, if the length is 6.5, the width would be 7.5, and that would give us an area of 48.75. If we were at 6.9 for the length, that means the width would be 7.1, and I'm getting 48.99. I will go ahead and put 7 on here for reference. If it's 7 for the length, it's 7 for the width, so our area would be 49. And then when we go to the other side of 7, maybe we could do like 7.1. We could just use the same numbers we used over here. We'll get the same area. So the point of this is to say, as you approach the length and width both being 7, that area approaches 49. So the max area is 49 square units. A limit doesn't always mean a maximum value, anything like that. So I don't want that to be confusing to you. But what a limit is where's the graph approaching? So that's the definition right here. If f of x becomes arbitrarily close to a unique number L as x approaches c from either side, then the limit as x approaches c of the function f of x is L. That's your limit. In other words, since from both the left and right, we approach 49 up here is our area. So we know that that happens when it's 7 and 7. All right, as we jump ahead here, your next slide, and I've actually split it up, and sorry the print is so small on yours, but your next slide shows some properties that come into play. These are all in your textbook as well, so if you want to look some of these up or have a little bit cleaner view of them, you can definitely look them up in your textbook in the section 10.1. They're right there. It won't take you long to find them. But it's just some of the basic rules. And so we'll talk about what these mean as we move forward. This is the basic idea. If b is some constant real number, the limit as x approaches c of b, well, b is not going to change. But I'm going to actually not go into too much detail talking about either of these two slides right now. We'll use some of these properties and we'll address them as we need to, but they're there for you to reference. You can see we have sums and products and scalar multiplication, powers, quotients, all this stuff. And so we'll look at those as they come up. And we will be using them today. But I'm going to use a table method to evaluate. So let's look at number 2. And you'll probably want to use a calculator as you do these. So I'm going to just do an x and an output. You can call it y, you can call it f of x, whatever you want. But it says the limit as x approaches 3. So what we're trying to see is, as we get close to 3, what's happening on the left, what's happening on the right, and is it approaching the same place? So I might start with something like 2.5, and I'm just going to use my calculator to get these values. I'm getting 2.41 here. Maybe I'm going to creep in a little bit closer to 3 and do 2.9, and here I get 2.48. Now in this problem we can do exactly 3 and we get 2.5. Now I will tell you there will be problems where you can't actually plug in that value. Well, number 3 will be the first of those, but you'll see others as well. So in some cases we can't just plug it in, and we'll talk more about that. But on at 3.1 we're at 2.52. Maybe I'll go to 3.5 and I'm at 2.59. Now the point of this is to say, as I approach from the right or from the left, in other words, as my x values increase, that's from the left. As they decrease, that's from the right. You can see we're headed right toward the middle here, toward 2.5. So that is our limit. It's 2.5. Okay, now in that problem, you could definitely argue it would have been simpler just to plug in 3, and you'd have 5 divided by the square root of 4, 5 halves, 2.5. Now, we can't always just evaluate by plugging in limits, though. Sometimes we have to do a little more thinking, and so this would be one of those, because if I try to plug in a 5 right here, I'm going to have division by 0. So I'm going to go ahead and use the table method again. Now I know some of you may have noticed that you can factor this thing, and some of you may have preferred that method. I would actually kind of be with you, to be honest. But I'm going to do the same thing. It says the limit as x approaches 5. So I'm going to test values that are approaching 5. There's no like exact science to this, but you can basically just start picking numbers that get increasingly close to the number 5. At 4.99, I'm getting this value to be about 2.99. Now here's the thing, at 5, we can't really plug that in, so I'm just going to put a question mark there. We don't know what 5 is. That's kind of the thing we're looking for, though. And if you plug in 5.01, you'd get like 3.01 as your value. If we plugged in 5.1, we would get 3.1, and you probably could stop there. So again, the question is, what's happening right there? Because obviously the graph doesn't exist, but you can see as we approach from the left or the right that we're getting close to 3. So that is the limit as x approaches 5. And we'll talk about other methods. You can look at a graph to do that, and this one you could use a factoring method. So there are multiple ways. That's the table method right there. All right, and we're going to continue with our table method on these next few. So this is a piecewise function. It says find the limit as x approaches 8 of our function, and you can see the piecewise function here. Now the weird thing is, actually at 8 the value is 12, but everywhere else we use this rule 4x minus 7. So I'm going to basically just use the 4x minus 7 rule and pick some values that approach 8. So maybe 7.9, I get like 24.6. 7.99 is 24.96. Now again, we can't really do 8, because if we do 8, we'd have to switch over to this rule. And honestly, weirdly enough, with limits, we don't care so much about if I exactly plug in that value. We care about, as we approach from the right and left, are the two sides headed to the same place? I think I have enough information here to, if I just look at this chart, I can see right in here, if I were to connect this, the limit would of course be 25. Now weirdly, if you actually evaluate f of 8, that would be 12, but that's not the limit. As x approaches 8, the limit is 25. A little bit of a distinction. You'll get better at it if it's kind of messing with you now. All right, so here we go. We have a couple of limits given to us, as both in terms of x approaching c. For f and for g, you can see the values. And these go back to some of these properties we were looking at a moment ago. There's nothing honestly too crazy about them. The limit x as x approaches c of 2 times f of x is just simply 2 times 5, or 10. The limit as x approaches c of f of x over g of x, you can just do division just as you would expect. And again, if you look back at those properties, you could see that. I don't know if I really should even change negative 5 halves to negative 2.5, but I did, so I'll roll with it. So 10, negative 2.5. And then the last one, again, we're using a square root. And then we're going to add in with, some scalar multiplication, but it's still, so the square root of 5 times 5, which would be 25, plus 2 times g of x, which g of x, that limit is negative 2. So 5 minus 4, the value there is 1. There are times where limits don't exist. We basically have three reasons why a limit would not exist. We're going to look at those three here. The first one is when left and right behaviors are different. So if you look at this piecewise function on number 1, you can see from the left we're approaching 6. From the right we're approaching 5. Those two limits don't meet at the same place, so left and right behaviors are different. Okay, number 2, unbounded behavior. So you can see this one here. They're both from the left and right. This function is approaching infinity basically, but we can't call it a limit when it's infinite. Those are oxymoronics. So is that a word? I don't know. But anyway, you can't have a limit when it's infinite. That doesn't make any sense in a lot of ways. And then the third one, we don't run into this one a ton, but it's a really weird thing we have going on here. And I would advise you to actually graph this. I would use Desmos probably, and just keep zooming in closer and closer to 0, the sine of 1 over x. You don't have to type in the limit, just type in sine of 1 over x. And look at that graph. It's a very confusing graph. It just looks like a big jumbled mess in the middle. And as you get closer, if you really think about the values there, it's a really strange thing. It's very confusing. It's hard to grasp that graph. But when you have this oscillating behavior where you have this crazy stuff going on in the middle, there's no limit. Now, fortunately, this doesn't happen all that often, but it is the third variety. As we go to our last two slides here, we're going to basically follow the same instructions on both, which are to use substitution to find the limit. Your notes might be in the opposite order of mine. That's okay. Just you'll figure it out. Start with A. So A is the limit as x approaches 3 of x cubed. Essentially, folks, anytime we have a graph that's continuous at the place where we're checking the limit, we can just use substitution. So in other words, if you were to graph x cubed, you have that cubic curve at 3, it's just going to keep bending upward. So there's no change in the graph. We can just simply plug it in. So 3 cubed, we know that's 27. And yes, it's that simple. All right, the limit as x approaches negative 2 of the function 4x, would just simply be 4 times negative 2, which of course would give us negative 8. Limit as x approaches pi of the cosine of x over 3x. Well, the cosine of x, when x is pi, cosine of pi, that would be negative 1, and then it's over 3 pi. And then finally, the limit as x approaches 25 of 2x plus the square root of x, that would be 2 times 25 plus the square root of 25, so 55 is our number there. And I know I'm moving through this fairly quickly, but it's just how quick these problems are. So we got 4 left. Let's keep going. The limit as x approaches pi over 2 of cotangent of x times the sine of x. Now, you could do some simplification on this first, but we're not going to worry about that. We're just going to do cotangent of pi over 2. Well, that's 0. The sine of pi over 2 is 1. We got 0. All right, and we'll keep going. I feel like you can basically do these as fast as you can write them down. So 2 minus 3 quantity squared, that's negative 1 squared, which would be 1. The limit as x approaches negative 2, so I'm going to go ahead and apply these. Negative 2 squared would be 4. We'd have minus 14 and plus 12. That's going to give us 2. And then finally, the limit as x approaches negative 2 of x squared plus 7x plus 12 over x plus 4. Now, one thing you'll note, we already dealt with the numerator right over here, so I'm not going to redo all that work. I'm just going to write this as 2 over negative 2 plus 4, which is 2, and 2 over 2, of course, is 1. Folks, that is all there is to it. This is your first day of limits. We'll get more in depth on what these look like and how they work in perhaps more complex situations, but I think you're going to get off to a great start. You guys have a spectacular day. Come to class ready to work.